Thank you. It's an honor to give, I think, the last talk. And thank you for sticking around. I'll try to be somewhat interesting if I can. I want to talk about why this doesn't work.
Because it's doing other things.
All right, then.
There you go. Maybe that'll make it work.
All right, we got one slide. That's good. Well, I want to talk about where it all starts, the foundations, the deeper understanding that we would all like about what's going on in the world, and particularly what's going on in the universe as a whole, how it got this way, and how any understanding that we might have of the universe as a whole could be applied locally to our own situations and to some of the phenomenon that we're interested in our daily lives. Bernie talked about the constants of the universe and physical laws of the universe, and I won't say a whole lot more about that, but it's worth just reflecting on the fact that it seems that there are a few numbers, a few constants, a few parameters that determine a great deal of what goes on in the universe and the phenomenon that take place within it. And these constants seem, at least, to be somewhat independent and rather arbitrary, and yet we know that in several cases these constants are very finely tuned to support the kind of universe that we see and the life that we experience here. And if they were different, the universe would have been different and we would not have evolved to have noticed this. So there's a question about how it got there, how those constants got that way. And by the way, how did all that stuff get out there in particular places? How did all this get to be the way it is? Even if we knew what those constants, those parameters were that determined the physical laws and the properties of matter and energy, we would still have this question of the initial condition. Why is it that the cosmic background radiation, the oldest thing we can measure, is not uniform? As a matter of fact, it seems to have some pattern to it. Big mystery. How did it get that way, and how are these parameters derived in the first place? Well, let me talk about oh, that's interesting. This is interesting. I think you have my presentation from last year or 2 years ago.
Well, I can't do anything about that.
There's a slide that wasn't in there. Well, it's all right. We'll go on.
Okay.
Yeah, there's something that got scrambled in the file. It's all right. Yeah, let's just do it this way. Yeah, I'm sorry, but we've got the wrong presentation. Can we look at the stick again? Yeah. Could the universe be some other way? The constants could be determined a lot of different ways. Here are 4 of them by some supernatural being. Perhaps they are determined at random, and there are a lot of different subuniverses that have different values for these constants, in which case we sort of invoke an anthropic principle. Those constants and those laws could have been in some way determined by our interactions with them, our observations. We created all by observing, somewhat like similar previous talk. Or the case that I'm more interested in, perhaps that these constants really aren't independent and arbitrary, but rather are mathematically derived and related in some interesting way. So I'll give a couple of thoughts about that. I'm reminded of Clarke's third law. And by the way, he added a fourth law in '99. For every expert, there's an equal and opposite expert. If you've ever been involved in patent litigation, as I have, this is very apropos. So I think it's any sufficiently advanced technology is indistinguishable from God. We're really not imaginative enough to think of what advanced technology, really advanced technology, could be like. And to say, as some would say, that they can't be here because it would violate the speed of light and too much energy is involved and all that kind of stuff is nonsense. They have complete control of time and space and a lot more things that we haven't even thought of yet. So if you think you have a guardian angel or some interaction with God, I don't see any way to rule out that as being interaction with really advanced beings and advanced technology. But beside the point, back to physical constants. Here are some of them. Bernie gave a nice summary of a particular list. Michio Kaku thinks maybe there are 19 numbers, enumerates those. John Baez counts 26 numbers. Martin Rees's book, Just 6 Numbers, which is a very nice read, derives the basis in an entirely different way using dimensionless numbers, the number of spatial dimensions and so on. Another interesting way of saying how many degrees of freedom are there. Maybe the real number is somewhere between 6 and 26. I don't know. The usual assumptions that are made before we start thinking about these things, I have some trouble with, not because the principles are necessarily invalid for any reason, but because of the way they're usually thought about. Materialism usually means there's stuff out there. There are things in space, whether those things are particles and fields or whether they are strings or some other abstract structure. I'm much more tending these days toward thinking about differences and boundaries and transitions rather than the objects. To me, the differences define the objects, not the other way around. And there's some precedence for this. I'll maybe be able to go into that a little bit more later. Reductionism, the idea that the whole is equal to the sum of the parts. People always say, no, something emerges when you get all the parts together that wasn't there among the parts. Forgetting that if you know the parts and all their interactions, you really do have the whole. Nevertheless, reductionism is not the only way to understand things, and I would like to promote more constructivism, that is, starting from first principles or no principles and building upwards, as well as reductionism, taking things apart and trying to figure out how they work. So the usual interpretation of that bothers me a bit. Randomness and the idea that there are truly causeless events at the core of physics, I've totally bogus that one. It seems to me that quantum measurement is not random at all, and there's a big mistake that we've been making by making that assumption. And it is an assumption in quantum mechanics. It just happens to work very well, so we believe it. But I don't think anything is truly random in the sense of being a causeless event, even at the core of physics. Cause and effects might be the most pernicious of these, in the sense that everyone thinks about cause and effect as a unidirectional thing, and this leads to the idea of time as a dimension and a flowing in one direction and so on. Bad idea. It seems to me that physics is telling us that everything is symmetrical in time, and that all relationships of a causal nature are bidirectional, and influence travels in both directions. If we take these assumptions and formalize them in some way, we usually get what's called a system of axioms. You could say the standard model of physics is a kind of set of formal assumptions, quantum theory, in mathematics, set theory, and predicate calculus, and so forth. So we tend to formalize this, and one might say that the more complex, well, let's say the less complex the set of axioms and beliefs are, the more likely it is that we're close to the bottom, that we're close to really understanding something, we're closer to bedrock. And the more complex things are, the reverse. So here's an example from mathematics, the Zermelo-Fraenkel and the axiom of choice set theory. 8 axioms, 2 of which at least are infinite axiom schema. Now, I ask you, does this look like we really understand the foundations of set theory? Or maybe sets are not such a good idea in the first place, which is where I go. Henry Poincaré said later generations will regard set theory as a disease from which one has recovered. Well, we haven't recovered yet. This is really one of the most fundamental things that are taught in mathematics. Congruent versus deep models. A congruent model is really a kind of a theory. It's an abstract something or another that we sometimes try to tune to be the same shape as whatever it is we're modeling. And so the more tuning is necessary, that added assumptions and FUD factors show up. And this is not necessarily explaining things, but merely modeling them, so we can do stuff and try things to the model that will then be reflected in the real world somehow. Whereas a deeper model has something that's simpler and is really more fundamental and more like how it really is, how the phenomenon or whatever it is actually generated, and tells us something more about its place in the world. Here's some discrete physical models that I think are really becoming more and more interesting. String theory hasn't quite paid off, but still there's something very importantly correct about it, even if it's not the whole story. Even in the standard model, group symmetries as an abstract idea can model 3 of the 4 forces, at least in some respects. Some of you may have seen causal dynamical triangulations, a terrible name if I've ever heard one. It's the cover story in Scientific American this month by Renata Lowell and some others. They claim to have derived from first principles the dimensionality of our space, 3 plus 1 or 4 dimensions. Questionable again, but I bring these forward just to say here's an interesting direction, and this kind of thing is what we ought to be looking at. Garrett Lisi and the E8 Lie algebra showed up as a possible candidate for a theory of everything last year, and Stephen Wolfram's New Kind of Science, which tries to explain everything in terms of cellular automata, again a very abstract notion at the base of it all. Here's the E8 theory, 248-dimensional Lie algebra. If you decompose this into various parts, subalgebras, Lisi would say that you get a very good correspondence to gravity, the forces, particles, and so on. Some people who know a lot more group theory and mathematical physics than I do have said this really doesn't map well, and it's not the answer, but it's a good try. So let's go to the other end of the spectrum, the simplest possible thing. What's the simplest possible thing we could imagine in the abstract? What's the starting place for everything that we must all share? And the answer, I think, is nothing. The void. And I don't mean the vacuum, the empty set, any of that kind of stuff. I mean nothing. Suppose we take nothing, we take the smallest step we can away from nothing. What would that be? Something. It doesn't have a name. It's not nothing. Okay, that's the first distinction. This is from G. Spencer Brown's Laws of Form. 2 distinctions can be made in 2 different ways. Cardinality and bosons flow from the first, ordinality and fermions from the second. So I think we're early on to something here. Some friends in Great Britain took this idea, which they developed separately, by the way, not from Spencer Brown, and tried to make a hierarchy of groups by instantiating the number of different things you could distinguish at each level, 2, 3, 7, and 127. The total number of symbols then is 2, 3, 10, 137, and really big. Now, this caught their attention because 137 is very close to the reciprocal of the fine structure constant, and 310, 137, and really big are something like the ratios of the strengths of the 4 forces. So this group has been looking to this quite a bit further than I can tell you about here and now. Again, I don't know whether this is going anywhere or not, but it certainly is interesting. Stepping to relativity, everybody knows that Lorentz transformation, or the Lorentz factor, is very critical and connected to lots of things in physics, as you can see from this diagram in Lucas and Hodgson's book. And they go into this book and derive Lorentz factors from a wide variety of different viewpoints. So there's something very important about the Lorentz factor. But I'd like to see it described and derived discretely. So here I have an object and the very, very simple notion of motion. That is to say, if it moves to the right, I count +1. If it moves to the left, I count -1. That's the simplest possible definition of motion I can think of. There's no rulers here, there's no clocks. When it moves, I tick my clock. If it moves in either direction, I tick my clock. And I keep track of, by counting these dimensionless things, how far it's moved. Here's the number that it moved plus, minus the number it moved minus. That's kind of a distance. The number it moved plus the number of times it moved in the other direction. And that's sort of a time. But we have no independent clocks whatsoever. So we turn that into a probability using the sum of these counts, and for simplicity in the algebra. And we can note right away there's a maximum velocity, which is 1 step per tick. If all the movement is in one direction, that's plus c. If it's all to the left, it's minus c. Now let's take two such things and try to add the two velocities together. This is like firing a gun from the front of a rocket ship, let's say. So we're going to watch just the second object, which is moving in a similar way but relative to the first object, so that these things add up. So I add them up. Here's the first velocity, here's the second velocity. And look at these two terms right here. When number 1 goes in to the left and number 2 goes to the right, we don't see anything because they cancel each other out. When number 2 goes to the right and number 1 goes to the left, those are canceling, and we don't tick our clock either. No time passes. So we do the mathematics on that, just a little simple algebra gives you this answer, and sure enough, 1 plus V1 V2 is in the denominator. So all steps are still size 1, c is equal to 1, and when you add the velocities together, you get exactly the factor that special relativity would tell you. Can we derive all of special relativity from this idea? I don't know. Haven't done it yet. Stay tuned. But the idea is that we started it with something extremely simple before the usual notions of space and time, and we got to something very quickly that gives us special relativistic additive velocities. Summarizing, the constants seem arbitrary, but they might be purely mathematical, and there might be a lot to be learned about them from studying them as abstract mathematical objects and deductions. I'm advocating construction rather than or in addition to the usual reductionist approach. Combinatorics and so forth seem to be very important. Suggesting the idea of distinction or difference as prior to object and maybe the ultimate origins, and the idea of discrete motion from pre-space and time and relativistic velocity addition. May I ask you a question? How many have ever heard of this discrete derivation of velocity addition before? Nobody? Okay. Thanks. It was due to Irving Stein and Tom Etter, as I may have said, and we're exploring that a lot further. We're always seeking funding to continue this research, so if anybody's interested, please let me know. Thank you.
Minutes for questions, and it looks like Dave Leiter got his hand up first.
Richard, this is more an observation than a question. One of the first books that I read entering into this whole realm, and I think I remember it correctly, was called Cosmic Consciousness by Maurice Burke. And what he predicted was that humanity was gradually becoming more and more and more intelligent. And I'm almost seeing that happen between the speakers and the audience. We're kind of gathered for that purpose and because of that growing ability.
It's a great sentiment. Thanks.
Okay, I sort of thought the speaker might have something to say in response. Any other questions?
I did.
I'd like to know what the implications are of the so-called cosmic axis of evil on your model. This idea that the universe it's not distributed evenly. You mentioned it briefly at the beginning of your talk, the background radiation.
Yeah, the background radiation seems to have some kind of a pattern in it, and there's an area where it's kind of sparse. I have no idea. It seems to me no more interesting than why is that galaxy over here rather than over there. But there's got to be a ton of information provided from someplace. So where did that come from is a very good question. But on the other hand, if I gave you a huge number, let's see, a huge integer that was, I don't know, 10 to the 100th digits long or something like that, could I ask you to tell me how much information is in that integer? In other words, how much would it take in information terms to distinguish that integer from all other integers of the same size? Well, it might take a while to figure out whether or not that was a highly composite number I gave you, or a prime, or what. And the amount of information contained in a very complex thing is not always clear. That's my point. So if you think in terms of really, really, really huge numbers, it might be that there's less complexity required to specify this universe than we would first think. I don't know. Maybe there's a lot more patterns that we have not discerned yet, both mathematically and physically.
I'm going to get in trouble for glossing the cosmologists, but the question about the fluctuation in the background radiation is the current explanation for why that galaxy's over there.
Yes, yes, right.
And this one's over here. And there was a literal conversion experience in 1990 when the Kobe data was presented at that meeting in Florida, and they all of a sudden became big bangers.
As you stated, randomness is an assumption that most scientists just take for granted. And yet you and a few others, including myself, seriously question that assumption. How is it that you have come to that conclusion, if you can tell us briefly? And what significance does that have for the evolution of the framework that you're taking?
How did I get to the dark side? Well, first of all, quantum randomness has been the most controversial kind of thing contained in the quantum measurement problem since the beginning. Even the founders didn't like it very much, and yet it works so very well. But I was, I guess, first started thinking about this by some physicists. The one that comes to mind, it might not have been the first that I read, but anyway, Cerf and Adami, Nicholas Cerf and Chris Adami at Caltech, wrote a paper about this that's been widely ignored. And there are some other justifications for it in purely quantum theory terms. So that got me started. Then I started to think about it more and look at the evidence from psi for backwards causation. And for backwards causation, this suddenly solves the problem. So it clicked together for me, and the more I look, the more I see evidence that things are symmetrical in time. Preparation, measurement, exactly symmetrical. If you think about that for a while, and I think you have, a lot of things clear up.
Okay, unfortunately, we're out of time for questions or discussion, so let's thank our speaker.